Okay, as promised, we're actually going to work out the chi-square, this very, very simple one. In the course of doing it, I'm going to try to elicit from you some intuition, some sort of sense about what it means for two variables to be independent. These are the data that you saw earlier. Everything shrunk. If you have a difficulty seeing it, remember that your notes from last time should serve you well, because nothing has changed. I just wanted to get everything on the board at the same time. So we have the Obama-Romney variable, and we have the gender variable, and observed frequencies 30-20, 20-30, an set of observed frequencies that appear to make it such that we would want to conclude that there's a gender gap. Women, 30 of the 50 women, 30 of them, voted for Obama, 20 males. You can look at this a different way. 30 women voted for Obama, 24 Romney. Any way you look at this thing, it appears as if there's a gender gap, and what we want is a little statistical inference about this, give us some leverage on the question of whether this observed result with a very, very small sample, 100 people, and again we are assuming this is a simple random sample of 100 people, whether it's arrived by chance, whether it is a statistical anomaly, or whether instead we can be rather certain, and to what extent we can be certain, that it's characteristic of what we had observed if we sampled over and over and over again, or better yet, if we had all of the data, all American voters. So, again, everything up here is as it was before. Things are abbreviated. The expected frequency here, have row marginal, some column marginal. Those concepts introduced in the earlier discussion of contingency tables more generally, we're now going to work a chi-square. First, using your sense, this is 50-50 Obama-Romney split, and a 50-50 split on gender. If these two variables are independent of each other, do you have an intuition of what belongs in the interior cells? That is, what should be here instead of 20-30? What numbers should be in? That's the question of the expected frequency. The expected frequency is the expectation given that the two variables are independent, which is a very strong assumption. Some people can get this right away. Some of you won't. But the answer is going to be 25 in every cell. This is a very contrived example, and you shouldn't expect in working chi-square problems, you shouldn't expect things to work out quite this neatly. But there's an illustration here, independent of the mechanism by which you calculate these normally. There's an intuition in here that you need to grasp, and that is, if you had 50 Obama supporters, 50 Romney supporters, and 50 men and 50 women, and these two things, gender and vote choice, had nothing to do with each other. That's what independence means. Recall up here from the probability discussion, I've got vote, V, G is gender, and I'm looking at the probability that vote equals 1, that is Romney, given gender, simply being equal to the probability that vote equals 1, that is Romney. You've seen that before, and it's a question mark. Are these two things independent? Well, if they are, if they were, you would expect, right? You would expect that women and men would split equally between the two candidates, and that's not what happened. For chi-square, this is shrunk, but this is FO, frequency observed, minus frequency expected, divided by frequency expected. We're going to square this, and we're going to run this calculation for every cell, every single cell in the matrix, and it's going to turn out to be the same thing every time. The next video will show a more realistic example where things aren't equal. This one's very easy to do. So FO minus FE, 30 minus 25 is 5. That's squared. 5 squared is 25. divided by the expected frequency, which is 25. 25 divided by 25 is 1. So the quantity, recall that we're going to sum across the cells for that cell is 1. And it's the same thing here. 20 minus 25 is minus 5, but if you square it, the minus goes away. It's also 25. It's also 25 when squared. So you divide through by 25, and here you get 1 as well. And the same drill you see is happening in each cell. So this calculation, whole calculation for each cell, is going to give 1. And chi-square for the table is simply summing across the cells. So 1 plus 1 plus 1 plus 1 chi-square equals 4. Now what that means, it comes with a p-value. We've seen that before. P-value that will sort of correspond to the confidence or uncertainty, as we talked about, that you have about this result, generalizing what appears to be a gender gap, suggesting that these two variables are not independent. And we want to know how secure that inference is from the sample of 100 people to the whole population, perhaps even a million. I have over here a table of critical values. Before computers, people used to do this by hand and refer to real tables of critical values. The defined critical value is associated with a different p-value, and they are here. This is p of 0.10. This one we've talked about the most. It's the magical or highly unfortunate number 0.05. That corresponds to the 95% confidence interval, 0.05. And then we have even a more secure result here of 0.01. So I'm telling you which values of chi-square correspond to each of these three p-values, given different degrees of freedom. I'm going to leave this up for when we do another larger chi-square problem subsequent to this video. I'm going to leave this up because we'll travel a little bit inside that table. We have a chi-square of 4. Where does it fit here? It's going to fit somewhere here. Can you see that? This value is 3.84, and this value is 6.63. I've got here, mentioned this last time, degrees of freedom defined in the table by the number of rows in the table minus 1 times the number of columns in the table minus 1. So this is a 2 by 2 table. 2 rows minus 1 is 1. 2 columns minus 1 is 1. So that's going to take us here to degrees of freedom. And we're going to see that our 4 is larger than the critical value associated with 0.05. The sort of strict frequentist interpretation then of this chi-square is that it is statistically significant at the 0.05 level. We know already from earlier videos and work together in class that this norm is just a norm and doesn't have any real basis in science, and yet it does tell us something. It tells us that if we took 1,000 samples of size 100, right, 950 of them would give us a result that suggested that these two variables are in fact not independent. This is, to the strict frequentist, a statistically significant result, and it's nicely illustrative of the power of inference. We only have 100 people here, and if they were selected at random, if these were real data, and they were selected at random, we'd be able to make an inference about an enormous population from a very small number of people. A little bit of review before moving on to another problem. Let's say again the column marginals here, row marginals, I didn't write that. They are here, and this thing comes with an exact p-value that you'll get on a computer when we do problems like this in class, which if you're watching this video in sequence, then we're about to actually do some in class using R. So I'm going to erase, get out the trusty wipe. Actually, we're going to stop here, and then I'll tell you something else in another shorter video.